Hello students, welcome to my channel. So in this video we will be learning about shear force and bending moment diagrams. Now this is a topic, if you are a mechanical engineer, if you are a civil engineer, you should be very thorough and very conceptually clear with this topic, right? So in this video we will be discussing the concepts, the basic concepts related to this particular shear force and bending moment diagrams, and in the next upcoming videos I will be uploading problems based on this, right? So without any further delay, let's start. So for studying shear force and bending moment diagrams, let us first look at this diagram. So this is a beam, this is an I-beam basically, okay? So in the left hand side we have a support, we have a hinged support, and in the rightmost we have a roller support, right? This is our longitudinal axis. I have written LA over here, and what we will do is we will put some load like this, okay? So after applying this load P, let us try to analyze what is happening, what changes is happening in this beam. So first of all, the very first thing we will observe after we put this kind of load is this, right? This phenomena is called sagging. S for sagging, S for smile. This is a symbol of smile, so this is sagging. If you observe something opposite like this will be hogging, right? So we will like in the physically we will observe sagging phenomena. So what I have done is I have considered this small portion in green to analyze, okay? So I have drew this small portion, I have magnified this small portion over here. So let us now try to analyze this part. So if you carefully see, that is the upper portion of the beam. This is the upper portion of the beam is under compression basically. See, the area have reduced, right? Initially it was a rectangle, right? But now the area has reduced, right? So in the upper portion it is under compression, but on the other hand we can see the lower portion is basically expanded. So we can also say that the lower portion is under tension. So we will write here compression C, and here T and T. Or you can also say that the upper portion is under compression stress and the lower portion is under tensile stress, okay? So now if we want to draw a stress profile of this particular diagram, we will see something like this. Let us say we will basically drawing a stress profile, right? So this is the mid of the beam, that is this, okay? Sorry, this is not symmetrical with this one, right? But see, the upper portion is under compression, so the velocity profile can be, we can draw this like this, right? On the other hand, the lower portion is under tension, so we can draw the velocity profile like this. So I hope this much is clear, right? Now let us do further analysis of this beam. To do the further analysis, basically now we will doing the analysis in the molecular level, okay? So basically for this we need to cut this beam into sections. So what we will do, we will basically cut the beam like this, okay? So let us say this is my section X, right? So now we will analyze this part in a 3D diagram. So basically I have drawn this like the opening, like this side, the left hand side like this, okay, in a 3D diagram. So what can we observe? We will observe something like this. So if you want to plot this thing into this 3D diagram, how would it look like? Let us see. So we will be getting something like this, right? So in red I have tried to plot the compressions that is acting in the inward section, see, and the green ones are the tensions, okay, acting in the bottom portion of the beam. So can you guess something? So what will be the result of this? So if you try to analyze the result, see, one is on this side, we can say on this side, and the other on this side. So it will result in a moment, basically. Moment in what direction? Moment in this direction, right? So in a simplified way, if you want to plot this thing in the 2D diagram of our beam, so it will be nothing but it will be like this. So this will be nothing but the moment, okay, which is generated due to this load P, which is acting perpendicular to the the longitudinal axis, right? So this is the first thing. So due to this load, we will get something. We will get a moment. Basically, we will get a moment like this in any sections of the beam, okay? And the cause of the moment is this kind of bending, okay? There will be another phenomenon. So what will be that? So another case will be this. This is known as basically shear force, right? Which will be acting in the downward direction, perpendicular to the longitudinal axis and parallel to the surface. This is the surface which we have sectioned. So it will, the shear force which will be acting is in the direction perpendicular to the longitudinal axis and parallel to the surface, right? So in conclusion, we can say that due to a force P in this beam, basically two phenomena are generating. One is the moment. I have already told you why is the moment is generating, right? The moment is generating due to bending of the beam. If we when we are applying a load, the beam is bending, the upper portion is getting compressed, lower portion is getting in a tension, okay? So for that we are getting a moment like this. This moment is nothing but this is actual bending moment. So in the topic of shear force and bending moment diagram, we now know what is bending moment, which is causing a moment which is causing due to bending, right? This is the first one. And the second phenomena which is happening is this shear force, okay? So if you want to distinguish between bending moment and shear force, so this is the thing. So shear force is forces which are acting parallel to the surface, perpendicular to the longitudinal axis. See, these are parallel to the surface and perpendicular. We have your longitudinal axis here, right? Something here. So basically these are perpendicular to the longitudinal axis, okay? And bending moments are what? Bending moments are the moments which are generating due to the forces that are acting parallel to the longitudinal axis. Here we have perpendicular to the LA and here we have parallel to the LA, right? So bending moments are the moments which are causing due to the forces which are acting parallel to the longitudinal axis. That is nothing but compression and tension. So these two will give rise to a moment which is called bending moment. So basically, if you section this beam, we are getting two phenomena. The first one is moment, and the second one is shear force. The shear forces are acting in the downward direction, right? So we can represent this like this, right? So one thing to note over here is if we are concentrating on this diagram, that is if we are cutting the section from the left, we are getting something like this. That is a shear force acting downwards and a bending moment which is clockwise. Which is anti-clockwise, right? So what if we cut the section from the right? Okay, so this one was from left, and let us now cut the section from right. So this section is cut from the right. So what will be the phenomena over here? So see, if we talk about the shear force, that will be unchanged, that will be acting in the downward direction only, like this, right? But if we talk about the moments, if we talk about the bending moment rather, what will be the bending moment? The bending moment will be in the opposite direction, that is in the clockwise, in a clockwise sense, not direction, sorry, in a clockwise sense. This is not a direction, this is sense, right? This is anti-clockwise sense. I'll write ACW, and this is basically clockwise sense, that is CW, right? So why this is basically theoretical thing. Okay, why this is theoretical? This is theoretical according to Newton's third law of motion, that is, to every action there is an equal and opposite reaction, right? So if we are now considering the section from left we will get to see that the bending moment is in a anti-clockwise fashion. But on the same time, if we consider the section from right, it will be in a clockwise fashion to counter this action. So this is basically action and this is basically reaction. Now let us look at the types of loadings that we can see in case of a beam. So the very first one is concentrated force, or basically we can also call it point load. You know, as the name suggests, the force will be acting only at a point, right? The second kind of loading that we can have is a UDL, or we can say uniformly distributed load. Okay, so basically in this case all the portions of the beam will be under a equal force, right? So let us say the force acting in each unit of the beam is W. So basically the force will be acting, you know, in each unit W force will be acting. So we can write W per meter. So what will be the total force acting on the beam? It will be nothing but the W into the whole length. So let us say the length of the beam is X. So the whole the total load that will be acting on this beam is W multiplied with X meters, normal, you know, unitary method. And you know, you should be knowing that the total force will be acting, will always act, in case of a UDL, it will always act in the middle of the beam. In the middle of the beam, in middle of the UDL rather. Okay, the concentrated force, that is the resultant of the UDL, will always act, you know, at a point, you know, which is in the middle of the UDL. Okay, that is x by 2, that is at the distance x by 2 from the origin. If you consider this as your origin, so from the origin it will be from a distance of x by 2. Okay, the third kind of loading that we can have is uniformly varying load, that is UVL. Okay, so this is a UVL. We will be solving problems on this. I'm just discussing the types of loadings which are available. Okay, and the fourth one, not the least one, that is concentrated moment, right? Concentrated moment. Okay, so we will be solving, you know, problems on each and every cases. We'll also be solving problems, you know, based on the combination of these loadings. Okay, so let us now talk about the types of supports. Okay, so we can have three kinds of supports: bent supports, also known as hinged support. Okay, roller support and fixed support. This is 1, 2 and 3, right? In case of the pin support, we will have no vertical or horizontal displacements, right? It cannot displace horizontally or upwards, that is vertically or horizontally. Okay, the only degree of freedom that it can have is rotation. So basically, since there are no vertical and horizontal displacements, so we will have reactions, right? So we will have two kinds of reaction, that is one on the vertical direction, and one at the horizontal direction. So basically, since we don't have any displacements in vertical and horizontal directions, the only thing we will have is the reaction forces acting at the support. In the second type of support, that is roller support, we will have only horizontal displacement, no vertical displacement, only horizontal, that is either in this side or in this side. So we will have only horizontal displacement, and we can also have rotation. So here only one degree of freedom is restricted, that is the vertical displacement. So in the case of roller support, we will have only vertical reaction, right? Okay, the next kind of support is fixed support. We will have no displacement, no rotation. So we will have three kinds of reactions, that is one in the horizontal direction, one on the vertical direction, and one is the reacting moment, right? So these are the reactions which will act on these three kinds of supports. So let us now look at the steps to draw the SFD and BMD, that is the shear force diagram and the bending moment diagram. So the very first step is to draw the FBD of the beam, okay, the free body diagram of the beam. The second step is to determine the reactions, that is what kind of reactions can we have. We can have forces. We have already saw in my last page, that is this. We can have forces, that is reaction forces. We can also have reaction moments. So if reaction moments are present or if reaction forces are present, we have to determine those reactions. How can we do that? We can do that by applying the equilibrium equations, that is the summations of the horizontal forces is 0, the summations of vertical forces is 0, the summations of a moment, the summation of a moment along a point is 0. So by using these equilibrium equations, we can find out the reactions. And the very last but not the least step is to determine the internal shear force. Now we now have to determine the value of shear forces and the bending moments along the beam. And after we determine the shear forces, the bending moments, we can plot the same in the so-called SFD, that is shear force diagram and bending moment diagram. So we will be seeing the steps in details in the next video, where we will take few examples based on how to draw the SFD and BMD. So now let us talk about the sign conventions that we will be using in solving the SFD and BMDs. Okay, so let us suppose we have a beam like this, and we have cut this beam like we have a load P, and we have cut this beam in this fashion, right? So consider in only one portion of the beam. So I will be talking about the left portion only. So if on the left portion you have a shear force which is acting downwards, this is a shear force, right? If you have a shear force acting downwards and a bending moment which is in the counterclockwise or in the anti-clockwise fashion, and on the other hand, if we consider the right side, if we have shear force which is acting upwards and the bending moment is on the clockwise fashion, then we will say we will have a positive sign convention. So this is basically a positive sign convention. And if we have the opposite, we will have a negative sign convention, that is shear force acting upwards in the left side of the beam and the bending moment acting in the clockwise fashion. And same, let us draw the reactions over here, that is shear force on the right portion will be in the downward, and the bending moment will be in the counterclockwise. So if we have something like this, then we will have a negative sign convention. Okay, I think I did a mistake. I'm so sorry for that. I did a mistake in the previous portion of my video. I have told you that this is basically in the downward direction. So this was the action, right? If you cut the beam from the left side, this is, I have written now, this is from left. So if you consider the beam from left side, this will be in an anti-clockwise, right? So this will be not downwards, and the shear force here will be downwards. Okay, so as a reaction of this, the shear force from the right will be in the upwards and not in the downwards, right? So it was a mistake from my side. I really apologize for that. So please do correct it, guys. Please do correct it. Okay, you can also have another approach to this. That is, suppose we have a beam like this, and suppose there are forces which is causing the beam to sag. That is, this is a case of sagging. Okay, so in case of sagging, we will have a negative sign convention, and in the case of hogging, this is a case of hogging, right? In the case of hogging, we will have a positive sign convention. This is positive and this is negative. Okay, so in case of sagging, we will have a positive sign convention, and in case of hogging, hogging case, will have a negative sign convention. This sign, the concepts of sign convention will get very crystal clear in the next video of mine, where I'll be demonstrating this with the help of an example, right? So students, this is it for this video. So if you like the way I teach, please do support me by subscribing to my channel, liking the video, sharing this video, and stay tuned, because I'll be uploading many problems, that is about 5 to 6 problems based on this SFD and BMD, and after I'll be creating a playlist for this. Okay, and I'll be completing the syllabus, the entire syllabus of strength of materials or the mechanics of materials in my upcoming videos, and also I'll be covering thermodynamics, fluid mechanics, and subjects related to mechanical engineering. So make sure you do support me by subscribing to my channel, and till my next video, see you.